Welcome back, students. In this video, we are going to talk about cells and EMFs and internal resistance a little more. We are going to see what happens when you connect cells in series and also when you connect cells in parallel. I told you that there is a subtle difference between a cell and a battery. A cell is a single unit and a battery is an array of cells. When a few cells are stacked together, then you would call that stack, that array, as a battery. Okay? Cells can be connected either in parallel or in series. We will first talk about what happens when you connect cells in series. Let me start with this. Okay? First of all, let us suppose that I have a cell like this. Okay. And now I am going to connect another cell in series. Another cell in series. That cell is like this, right? So say that's like that. Okay. Well, I'm going to take this cell 1 and then this is 2. I'm going to connect cell 1 to 2. See, there are two ways I can connect it. I mean, even if you connect them in series. One thing is that I will take the positive end of it and then connect it to the negative end of it, like this. And then the negative end will be like this. Okay? So take this positive and connect it here. So that is one arrangement. What's the other arrangement? The way I can connect it is like this. The positive is, I can take the negative end and then connect it to the negative end as well. Okay. So there are two ways in which I can connect cells in series. So when I do that, I am not considering the internal resistance yet. Okay, I'm just going to give you. I'm going to give you how these things will work. Okay. What would be the net voltage out of this in both cases? Okay? So that would be the objective. Okay. First of all, to do this, we will first talk about cells in series. Okay. I'll take this. See, when I say take a cell, I told you that it will have an EMF and will also have an internal resistance, right? So if you take a cell, let's say I have a cell like this, right? This is a cell like this. Okay, so you have positive and negative there, right? Okay, so you have a cell like this, and if you take the normal the battery cell, so this would be positive and this would be negative. There will be a group there. And I can take one more cell like this, and then this will be positive and this will be negative. So notice it, I am connecting the positive end to the negative end. So this is how the cell looks like, right? So I am connecting it. So how do I represent this basically? So if I take this cell will have an EMF and also an internal resistance. So I will put it this way. The circuit is going to be like this. It will have an internal, and there is an EMF. I will call this as epsilon 1, and then we can also have a resistance R1. So this cell will have that. And then let's look at this cell. This cell also will have an EMF and then an internal resistance. So this EMF is E2 and then this is R2. So I'm going to connect this now. Okay. So when I do this, let me remove this so that things will become much clearer for you. Okay. So it's like this. So you have E2, R2, and E1, R1, Now I'm going to connect these two. So this is the arrangement of cells in series. But in this case, I have connected the negative terminal to the positive terminal of this cell. Okay? I'm talking about this one. But it doesn't matter, it will work for that also, but we'll do all that a little later. Okay? First, this is the arrangement. Okay. Now, let us suppose that I have another resistor. I'm going to connect a resistor across these two batteries. Okay. I will call this as this resistor or the load resistor. It may be a toy, it may be the remote control itself, that instrument. It can be anything. Okay. So that is the resistance you're connecting across this. Now, there is a current that flows through this. I. You can calculate the current very easily, right? If you calculate the current, what would that be? It's going to be equal to, if I apply Kirchhoff's laws, then I can find the current to be equal to epsilon naught E1, E2 divided by R1, R2, R1 plus R2 plus Rn. That's what I'll get. But let us suppose this. Okay, we will do it. We will do it now. See, how do you get this? The amount of current which is flowing through this. Well, there is no branch. Yeah, there is no junction, I should say. There is no junction. So, you notice here, it's like there is only one current that is flowing through it. And let me start from here and let me complete the loop. Okay, suppose if you choose I to be in this direction, then as I told you, using Kirchhoff's laws, this is positive, this is negative. And the current again will go in this way, so it enters this resistor this way, and then this is negative. And then here, this is positive and this is negative. So chosen the current direction, so then I assign the potential drop signs across the resistors. Now can I go complete the voltage now? Easy, right? So I can start from here and I will come back to the same position. I go here, so the voltage drop is positively because it's entering the positive thing, right? So it's I is the current, so the voltage drop is going to be I Rn. Okay, and here it's going to be I, same I R2. This is I to R1. Let's do it now. So I come here, it's positive I Rn. So I Rn. Then I come here. Then EMF. I'm entering through the negative terminal, right? So that is going to be minus epsilon 2. Okay? Then the current is entering the positive part of this battery because the loop is like this, right? So that is going to be plus IR2. Okay? So now, and this goes here. Then again I am entering the battery through the negative terminal. So that's minus epsilon 1. Then I go further here. That is going to be plus, right? Because I am entering through the plus part of it. So that's going to be plus I R1. So I come back to the same position. So that must be equal to 0. So what have we got here? I can take E1 and E2 to the other side, right? So E1 plus E2 is equal to I into R1 plus R2 plus Rn. Okay? And this is expression I get. And this one, cells connected in cells in series. What is my objective? My objective is to find an equivalent cell. Okay? My objective is to replace this with an equivalent cell. I have two cells here, but I'm going to replace it with one single cell. Then I need to find what would be the E of that cell and the R of that cell. Okay? This cell should supply the same current I to this resistor R. So that is equivalence, right? So I got two cells here, connected two cells, they supply I current to this R, this load resistance. Now the objective is to replace this with a single cell that will have a certain EMF and then certain resistance. Then what should be the EMF of that cell and the resistance of that cell that will supply the same current I when the same resistance RL is connected to it. Yeah, that is the equivalent circuit. Okay, now let's see what I will get here. Again, I have chosen current to flow through this. So this is positive, this is negative. Current will go like this. So this will be positive and this will be negative. Okay. So I was saying the potential drop symbols here, signs here, right? Now I can do Kirchhoff's law for this also. I can do it either this way or that way, doesn't matter whichever way I do, I'll get the same equation. But I'm going to do it clockwise direction. Again, I start from this point. So when I enter this resistor, I am entering through the positive point of that. So that will be I or then I come back, I enter through this cell, negative terminal, so minus E. Then I come back and then I enter this resistor, internal resistance through the positive terminal. So it's going to be I R must be equal to 0. So that's how voltage drop, right? So voltage is I R L here, then I R here. So that's what I've chosen. So notice here, if I take this E to the other side, it's going to be equal to I into R plus R. Okay? So it's the same current. This current must be the same as this current. Okay? So what is this current I? This I is equal to E1, E2 by R1 plus R2 plus Rn. Okay? That is the equation 1. Okay, but here, what is this current I? E by R plus Rn. Okay, so that is the equation 2. So what should I do now? This must be equal to this, right? Because I am going to replace this with one cell that will do the give me the same current when RL is connected. The same RL is connected in both places. Yeah. So can I compare now? So what is my E? My E is actually equal to E1 plus E2. Okay, that is my equivalent resistance. Equivalent EMF. So this battery must have an EMF which is equal to the sum of the EMFs of these cells, epsilon 1 and epsilon 2. You have to sum those two things. That must be the EMF of this cell. And what is the internal resistance of this cell? This R, again I am going to compare. Well, what I got here? R plus RL, this R1 plus R2 plus RL, this is common. So R must be equal to R1 plus R2. So R here must be equal to R1 plus R2. So I can say that when I connect two cells in series, and if I want to find the equivalent cell for this arrangement, then that cell will have an EMF which is equal to the sum of the individual EMFs of these two cells, and it will have an internal resistance R which will be equal to the sum of the internal resistances of these two cells. Okay, so we have done it for two cells. This will work for any number of cells, you can see. Okay? So now, if we connect say n number of cells, then E is equal to E1 plus E2 plus E3 all the way up to En. Okay. Then R equivalent resistance must be equal to R1 plus R2 is R3 and Rn. So I have to know the individual internal resistances of all these different cells, and if I add them all up, then that will give me the resistance I need to have for the internal resistance of that one cell I am going to replace all these things with. Okay. Likewise, the EMF will also be equal to the sum of the individual EMFs of all the cells, all the N cells. Okay. And that would be the EMF of this cell I have chosen to replace the whole thing. In that case, this single cell will provide this resistance RL with the same current I that all these cells get together providing RL with. Okay. So that is the idea. Hope this is clear to you. And coming back to this, now that you know how this is all getting added, let's come back to this one. Okay. Let us suppose this is E1 and then this is E2. Then what would be the equivalent potential here? Okay. That is going to be simply E1 plus E2. Okay. I'll try to explain that with a numerical example. Suppose this battery is say 1.5 volts. Okay, and this battery is, let's say it's 1.3 volt or something. So I'm going to add this, right? So what does this mean when you say 1.5 volt? Let's say one cell is 1.5 volt, and then another cell is 1.3 volt. What does it mean basically? It means that with respect to this terminal, with respect to the negative terminal, the positive terminal is 1.5 volts more. Okay, this will have a potential, but this potential is going to be 1.5 volts more than the potential of this. Okay, the positive is 1.5 volts more than the negative terminal. Likewise, in that case, positive is 1.3 volts more than the negative terminal. Okay. Now let me come back to this. Okay. Now I am connecting batteries like this. Okay. Note here, I have taken the negative terminal of one battery and I am connecting it to the positive terminal of the second battery. You see, this is a metal that is connected to another metal, and they would be at the same potential. Whatever potential I have here will be the same potential here, because they are single metal now. Okay, so this is a single metal. They become, they connected now. This part is connected. But what do you know? This is, if I say this is 0, for example, and this potential, what is it? It is 1.3 volts more than this. So 1.3 volts more than this. With respect to this will be 1.3 volts more. Okay. And then, what is this? It is 1.5 more than this one. This negative. But you have connected these two. So this point, the negative of this battery must be at the same potential as this 1.3. Okay. So you will have 1.3 here. Same 1.3 here, right? And the same. Now it has become a single conductor. So you connected them both. But with respect to this, what should this be? With respect to this should be 1.5. So there is 1.3 and 1.5. It should be more 1.5 more than this 1.3. So this potential now will become 2.8 volts with respect to this. I hope you understand this. When you take 1.3 volt battery, what does it mean? Which means that the positive terminal is 1.3 volts more than the negative terminal. And when you say 1.5 volts, then the positive terminal is 1.5 volts more than the negative terminal. Now when you connect these two, these two are at the same potential, same conductors, right? They are now doing single conductor, so you have the same potential. But this is 1.3 volt more than this one. If this is 0, that will be 1.3. or if this is 1, and that would be 2.3, whatever. Okay. So, but let me just take that to be 0, and then that is it's going to be 1.3 volt, and that would be the same potential here. Now it's 1.3. But what do we know? This one should be 1.5 volt more than this terminal. That is 1.3. Because of this is going to be at 1.3. So this must be 2.8 volt. Only then you can have 1.5 volt difference between these two. So you notice here they get added up. That's what you see here. So this is 1.3 and this will become 1.5. So you get 2.8. That will be the output voltage. Now let's talk about this arrangement. Okay, same, right? What do we know? Well, if this is 0, okay, this would be 1.3. Right? Okay. Now, you are connecting this negative of that battery to this battery. Okay. Now, these are at the same, both of them are at the same potential. Okay. So, what happens here? The same potential, but this is going to be 1.5 more than that. Notice, this is at 1.5 volt and this is at 1.3 volts. So what's the potential difference? 1.5 minus 1.3, that would be 0.2 volts. So you see they get subtracted. So when you connect negative to negative, then the potential of the battery will get subtracted. And if you connect negative with positive, then they get added. So that is exactly what's happening. You can do it two ways. Okay. As I said, the one way that I already explained. I said this is 0, so this is 1.3. So this will also be 0, that will be 1.5. So this plate is at 1.5 voltage and this plate is at 1.3 voltage. So the potential difference is 1.5 minus 1.3 is 0.2. 0.2 here. With respect to this is 0.2 volts more. With respect to this this plate, this will be 0.2 volts more. I can say that. Or I can say with respect to this is 0.2 volts less. I can say that too. Now, the other way of doing it is this. Look at this battery. It is 0, right? I mean, I chose this to be 0 and this is 1.3. I can do it the other way also. How can I do it? It is like I can take this to be at 0 potential. If this is at 0 potential, then this must be at minus 1.3 potential, right? Because the potential difference between this and this must always remain 1.3. Okay, so if this is minus 1.3 and this is 0, the potential difference is 1.3. Yes, 0 minus 1.3 will give you 1.3 volts. That's the potential difference. So if this is minus 1.3 and this must also be minus 1.3. But what we know? This plate is 1.5 volts more than this one. Okay, but it's minus 1.3. If I add 1.5 to that, then what would I get? I'll get simply 0.2. So, what is the potential difference again between this plate and this? This is 0, this is 0.2. So, 0.2 volts is the potential difference. In either way, remember this. When alternate polarity are connected, then the EMFs add up. The same polarities are connected, then you need to subtract one EMF from the other. Okay. Same thing. So E1 plus minus E2 is what you will get, because you are doing it differently, right? So effectively E1 minus E2 is what you will get. Hope this is clear to you. Okay, now let's do cells in parallel. Again, I'll take two cells and connect them in parallel. So the first cell will be like this. We have an internal resistance R1 and an EMF 1. And let me take another cell R2 and then 2. These are the two cells. We want to connect them in parallel, meaning that the positive terminal will be connected to the positive terminal and the negative terminal will be connected to the negative terminal. Now I got them in parallel. So now this is the arrangement, and this arrangement is going to supply current to an external resistance. I'll call this as RL as usual. Okay, so this will supply current I to that. Now this is cells in parallel. Okay, so I is the current that will be flowing through this load resistance RL, and this I will be contributed by both the cells, right? So there is a current, say I1, that flows through this one, and then I2 that flows through this side. So I1 plus I2 will give me I. So that's my first equation. I is equal to I1 plus I2. Okay. So this is going to be IR, right? Okay. What is the voltage across this? This would be, let's say, current. I've chosen the current direction to be this. So this is plus, this is minus. I've chosen the current direction to be this. This is plus, this is minus. I've chosen the current direction to be this. So this is plus, this is minus. Okay. Now we are all ready to apply Kirchhoff's law. What would be the voltage across this IRL? RL? That would be I into RL. Okay. I'll call that is the voltage across this, right? Between these two terminals. And I'll call that as V. So this voltage across this resistor, I'll call as V. Okay. Now let me apply Kirchhoff's laws. Okay. Now I can have two loops. Well, one loop is going to be this. Okay. One loop is a different color now. So one loop is going to be this loop. Okay. And then the other loop can be this one. Okay, these are the two loops I can use. Okay, I am going to use the first loop, the red loop. Okay, the red one, let's say I'll start from here and then I'll come back to the same position through the red loop. So this is IR, right? So that is V anyway. So V, first loop, first equation is V is equal, this IR, I am taking that as V. So that is plus, I am entering into plus, right? So that is V plus, I come here and then I go through this, right? So then I enter this one, negative. So that is going to be minus E2. And then, now what is the voltage drop across this resistor? I2 is the current flowing through this. So this is going to be I2R2. So this would be, it's entering through the positive terminal here. So plus I2R2. Then I'll come back to this position. So that is 0. So no more there. So that is 0. Okay. So what can I do? From this can I find I2? Well, I can take the other things. This I2R2 is equal to E2 minus V. So what is I2? I2 can be written as E2 minus V by R2. That's I2. Well, I'm going to do the same thing for the blue one. Okay. So I'll start from here and then come here, and then go and then take this route and then come back here. So the blue one, so this is for the red loop and this is the blue loop, is this. What happens here? Start. Again, I is the current flowing through this, IRL, which is equal to V, right? So I am entering this way, so positive. So V, then I come here and then I'm going to go this way, right? So I am entering this battery through the negative terminal, so minus E1. Then this is going to be I1 R1. I am entering it through positive. So this is voltage drop is I1 R1 here. So I am entering that resistance through the positive terminal. So that is I1R1. Then I will go back to that. So it is 0. So what will I get? What will be the value of I1 here? So I1, if I calculate, then all these things will go there. So E1 minus V by R1. That's my I1. Okay. So we got these two things covered. Now, what is I? I is equal to I1 plus I2. So I is equal to I1 plus I2. So what is I1? That is E1 minus V by R1, and then plus E2 minus V by R2. We will rearrange this a little. How I will rearrange? E1 by R1 plus E2 by R2 minus V by R1 minus V by R2. That gives me E1 by R1 plus E2 by R2. That is one term. And minus V into 1 by R1 plus 1 by R2. Okay. So that's my I from this circuit. So what is the objective for me? The objective is to replace this with a single E and then a single R. Okay, I am going to replace these two with a single E and a single R, and that should supply the same amount of current I there to the RL circuit, the RL resistance, right? So now, so what is the objective? The objective is this: I'm going to have a single EMF E and then a single internal resistance R, and that must supply to the RL resistor the same I that you are supplying there. Okay. Now, can I use Kirchhoff's law? Again, what is this? Voltage drop current is I. So this is positive, this is negative. This is again positive, this is negative. Going to let that. This IRL is equal to V, right? So this is IRL is equal to V as here. Okay. So that's about it. So these are the things that you have. So what equation can I form here? Again, I will take this point and then come back to the same place, and then let me use Kirchhoff's voltage law. So what is the voltage drop here? That is IRL, which is V. Is it positive? Yes, it is, because I am entering it through the positive terminal, right? So V, then I come here, I enter this through the negative terminal, so that is minus E, then I enter this through the positive thing, again, and that's going to be plus IR equal to 0. Because then what is my I here? My I is equal to, E will be positive there, minus V divided by R. So what's my I here? I can be written as E by R minus V by R. Okay. Since this side and this side must be equal, then I can compare these two equations. Okay. So this is equation 1 and this is equation 2. Then can I compare these two? When I compare these two, E by R, note here, when I compare these two, comparing 1 and 2, I'll get E by R is this term, right? E by R is actually equal to E1 by R1 plus E2 by R2. Okay. Now, what is V by R? Or V by R is this. So 1 by R must be equal to 1 by R1 plus 1 by R2. Take this term and compare. V is here, V and V are there. So 1 by R must be equal to 1 by R1 plus 1 by R2. So 1 by R is equal to 1 by R1 plus 1 by R2. Okay, this is the result of this calculation. Okay, so what can I do from this? How can I find E? Well, E is simply what is equal to E1 by R1 plus E2 by R2 into R. That's my E, right? So my E is simply equal to E1 by R1 plus E2 by R2 into R. But what is R through this? Looks like, no, so these two seem to be in parallel, the resistances. So R would be, what is R? So this gives you R is equal to R1 R2 by R1 plus R2, right? So that's what I'm going to use here. So this will give me E1 by R1 plus E2 by R2 into R1 R2 by R1 plus R2. Okay, so let me take LCM here. Take the LCM there. So R1 R2. So that will be E1 R2 plus E2 R1 divided by R1 R2 into R1 R2 by R1 plus R2. So this and this will cancel. So effectively E is equal to E1 R2 plus E2 R1 by R1 plus R2. R is anyway is equal to R1 R2 by R1 plus R2. So this is the expression for cells, two cells connected in parallel. This would be the effective EMF. If you know E1 and R1 and E2 and R2, then I should be able to figure out what this E will be using this expression. And then the R, the internal resistance R, will be equal to R1 R2 by R1 plus R2. So this is what you are going to get out of this. But you see, this expression is a little difficult to remember. But what can you remember easily? What you can remember easily are these two. Okay, what is it? So this is effective EMF and then it's effective resistance here. So now E by R is equal to E1 by R1 plus E2 by R2. Okay, and 1 by R is anyway 1 by R1 plus 1 by R2. So then you can find R from this, and you can find this term, then just multiply this R from here. Then you get the effective EMF. Okay, so this is very important. You see, we have done it for only two resistances, two cells, but even if you do it for any number of cells, you are going to have the same expression. Meaning that if you generalize this, with n cells, what is going to be my E by R, effective EMF by effective internal resistance, is going to be equal to E1 by R1 plus E2 by R2 plus E3 by R3 all the way up to plus En by Rn. Okay, so that would be this quantity. Then what is my 1 by R? This we know already. It's like resistors in parallel. So you are going to have 1 by R1 plus 1 by R2, 1 by R3, all the way up to 1 by Rn. So this is a very general result for n cells. Okay. Once you know this, it's very easy to remember also. They are in parallel. Okay. The cells are in parallel, which results in the effective resistance of the internal resistance. The effective internal resistance of the cell being equal to this. 1 by r is equal to 1 by r1 plus 1 by r2 plus 1 by r3 plus 1 by rn. Because you can connect this with parallel thing. Okay. So you get 1 by r. Then what is the new thing? It is the e by r2. E by r is equal to e1 by r1 plus e2 by r2 plus e3 by r3. Do this. So if you know e1 and r1 and e2 and r2, then you can find e by r just by adding those two terms. And now then you can also know r by using this expression 1 by r1 plus 1 by r2. So you can find e that way very easily. So remember this for cells in parallel. For cells in parallel, the resistors, the internal resistors act as if they were connected in parallel. So that would be the key. And then the next idea is e by r is this. You cannot forget it. Okay, e by r is e1 by r1 plus e2 by r2 and so on. These are known quantities. We calculate these things, and from that we find e and draw the circle. Done. So this would be the effective resistance, and this is the internal resistance, effective internal resistance, and then this would be that resistance, like a load resistance for any for a particular load resistance. This will supply current I. Whether you take it and connect it to this cell or connect it to this arrangement, the R will have this particular RL will have the same current both ways. Meaning this EMF is the effective EMF of this arrangement, and this R is the effective resistance of internal resistance of this arrangement. Hope this is clear to you. Okay, let's do a problem using Kirchhoff's laws. Okay, I'm going to do example 3.7. Determine the current in each branch of the network shown in figure 3.24. Okay, let me draw the figure and then we'll take it forward from there. Okay, this is example 3.7. Okay, this is one. There is a resistor here, and then this is another resistor here, and there is a battery here, and there is a resistor here, and there is one more resistor here, and there is a resistor here. Okay, so pretty much that, and this is connected to a battery. Okay, so let's put in the numbers. This is 4 ohms, and this is 2 ohms, and this is 1 ohm, and this is again 4 ohms, and this is 2 ohms. And this is 5 volts, okay, and this is 10 volts. Okay, so this is labeled as A, and then B, then this is C, and then D, and then this is E. Okay, I put it this way. I call this as E. So then they have also given the current relationships here. So they have already used the Kirchhoff's current law, and they come up with this relationship. So they call this current, see the current I1, this is called, I1 is in this direction. They've chosen this direction I1, and this is actually I2. So then this clearly, they're choosing this direction, meaning here this current is going to be equal to I1 minus I2. You can see that clearly. See, there are two things which are going out and there is one coming in. So I1 must be equal to this current and this current, right? So this is I2, so I1, so this must be I1 minus I2. So that is what they have done here. Okay. Next one, they have I3 going this direction, chosen this direction I3, and I2 plus I3. I2 is coming here, I3 is coming there, so something must be leaving, so that must be equal to I2 plus I3. Okay, and here this one they chosen this direction. Okay, I2 plus I3 is coming in, and this is going out. Notice it. Okay, so this is I1 is going there. So this must be I2 plus I3 minus I1. That's the current going through this. Okay, and here it is I3 must enter the battery and then leave the battery. I3 must enter. You see the amount of current that is entering the battery must be equal to the amount of current which is leaving the battery. Now the question is to find the current in each branch. Okay, what is the value of I1 minus I2? What's the value of I2 plus I3 minus I1? And what is the value of I2 plus I3 here and I3 here? So call it to find I1 there. So basically, if you look at it, there are only three unknowns: I1, I2, and I3. If I knew the three unknowns, then I can find I1 minus I2. I can find I2 plus I3 minus I1, and I can also find I2 plus I3. All that can be, all the current in all the branches can be figured out if I know the value of I1, I2, and I3. So I have three unknowns. How many? I1, I2, and I3 are the unknowns. So how many equations would I require? I would require three equations to solve these. Well, the current law has already been used, so that is why you get these currents here. Then I must be using the voltage law. Okay. For me to do it, I have to assign the voltage drops across the resistors first. Okay. So let's see which one would be the positive direction and which one would be the negative direction of the voltage drop. Okay. Then negative, positive point and the negative point of the resistor. The current is entering here, so this must be positive and this must be negative. That's fixed. So 4I2 would be like this. Then here current is leaving here, so this must be negative and this must be positive. This current must have entered there and left there. So I2 plus I3, that's the current, into 2 ohms would be the voltage drop there. Okay, and let me come here. I1 is going in this direction, so I1 must have entered here and left here. So that's plus minus. Then this I1 minus I2, this current is entering here. That's what I say. So that would be, this would be positive and this would be negative. And coming to this, I2 plus I3 minus I1 is the current that is flowing in this direction. So this must be positive and this is negative. That's where it enters the resistor. So now it is all fixed. The voltage drops are all fixed now. Okay. Now what do you need to do? You just need to apply the loop law. So there are three unknowns, then you require three equations for it. Well, there are many loops you can form. 1 loop, 2, and then 3. I can also form a loop like this, 4. I can form a loop like this, 5, and many other loops that may be quite possible. Okay, but I'm going to choose any 3. What's the condition? The 3 loops must cover all the branches. I should not leave anything open. Okay, the 3 equations must have covered all the branches. Okay, so first let me do this loop. Okay, let's do this loop. I'm going to take this loop first. I'll start from A, I'll go to D, and then C, and then back to A. Okay, so that's my first loop. And what is my next loop? My next loop can be this. Again, right? I'll go like this, right? I can do it like this. That could be my second loop. Then my third loop could be this. Okay, like that. Or I can do it the other way. Doesn't matter. Whichever way I do, doesn't matter. I can do it this way. Anyway, it's fine. Okay, either way is fine, doesn't matter. Okay, you see, then I covered these three, and then I covered these two extra, and then I cover, when I do this, then I cover this also. So I have not left any branch uncovered. I have covered all the branches of this circuit using these three equations. I require three equations because there are three unknowns, and those three loops will cover all the branches of the circuit. Okay, so that is done. Now let me start with this. Let me start with this ADCA thing. Okay, ADCA loop ADCA. I'll start here. This is how I do it. I'll start from A and come back to A again. So I1 into 4 ohms, right? So 4 I1. Is it positive or negative? It's positive because you see I am entering here. When I do the loop, I do the loop like this. So I enter this resistor through the positive terminal. So 4 I1. Then I come here. Then what do you get here? Well, I'm going to get I2 plus I3 minus I1. That is the current multiplied by 2 ohms. Okay. But is it positive or negative? It's negative. Notice I am entering through the negative terminal of that resistor. So just put a negative sign there. And let me come here. So what is flowing in this? I1 is flowing in this, right? This resistor. So 1 into I1. So 1 into I1. That's the potential drop. But how am I entering? I am entering through the positive point. So that is a plus. Okay. And then what happens? I enter through the battery. How am I entering into the battery? To the negative terminal. So that's going to be minus 10. Have I come back to A? Yes, I come back to A. So then that must be equal to 0. Okay. So now I need to rearrange these things. So I got 4 I1 and then minus 2 to minus I1. So plus 2 I1, 4 I1 plus 2 I1, 6 I1 plus 1 I1. So 7 I1. Okay. And then how many I2s? Minus 2 into I2. Is there anything else? Nothing. So minus 2 into I2. And then minus 2 into I3. Then minus 10 must be equal to 0. Then I can take 10 there, so it becomes equal to 10. So that's my first equation. Okay, for that loop. And then I can take this second loop. So loop ABCA. This loop. Okay. So I'll start from A and then I'll come back to A. And now it is I2 into 4. So 4 I2. Is it positive or negative? Well, I'm doing this loop. So I'm entering this resistor through the positive point. So that is plus. No problem. And then I come here. And then what is the current? I2 plus I3. I3 is the current. I2 plus I3 is the current. And multiplied by 2. That's the voltage. 2 ohms. That's the voltage. Is it positive or negative? Well, I am doing this loop, so I am entering this through the positive, so plus 2 here. Then I come here, then this is going to be I1 again, right? I1 into 1, so 1 into I1. Is it positive? Again, yes, it's positive. I am entering through the positive thing. Then what do we get here? Then negative, minus 10. I am entering through the negative point. Then I come back to this thing. So that is equal to 0. So we do this now. 4 I2. Okay, let me take I1 first. 1 I1 is any other I1? No. So I just take I1. I2, 4 I2, then 2 I2, so 6 I2. Anything else? No. Plus 6 I2, then plus 2 I3. Minus 10 is equal to 0. Then I'll take 10 there to the other side. So that is equal to 10. That's my second equation. Second loop is done. Then third loop, this loop. I have chosen this way, right? EBD. Loop EBD. start from here and come back to that. When I go here, then I enter it this way, right? I enter it this way. Well, okay. What is the voltage drop here? I2 plus I3 into 2. I2 plus I3. That's the voltage drop. Is it positive or negative? Well, I do the loop like this. So I am entering it through the positive point. So that is positive. Then I come here. I come here. So this is, again, I enter it through this point. What's the voltage drop? What's the current there? I2 plus I3 minus I1. I2 plus I3 minus I1 is the current multiplied by this 2 ohms. This is positive or negative? When I am doing the loop like this, I am entering the resistor through the positive terminal. So that is positive 2. Then I come back here. And there is no further drop here, right? There are no resistor. So I can ignore this current. Then I can come back to this voltage. I am entering it through the negative terminal. So minus 5. Okay. So I come back to E. So that is 0. I am done. Okay. So let us see how many I's, I1s and I2. 2 minus 2 I1. Okay. 2 into minus 1, so minus 2 I1. That is 1. Second, I2, I got 2 I2 here, 2 I2 here, so plus 4 I2. And then I got 2 I3, then 2 I3 here, so plus 4 I3, minus 5 is equal to 0, I take 5 there. Okay, so I got 3 equations, equation 1, equation 2, and then equation 3. Okay, so using these 3 equations, these are simultaneous equations, right? So using these 3 equations, I can solve for I1, I2 and I3. See, there are 2 ways of doing it. One is through general, the application of algebra, and the other one is through matrices. Okay, either way you can solve. You can form a 3 by 3 matrix and solve this equation, these 3 equations. That is one method, and the other one is just by figuring out how to do this. Through simple. For example, I'm just telling you. I'm not going to do it in full, but I'll tell you how to do this. I can express it I1 in terms of I2 and I3. Right? How can I do that? So, for example, minus 2 I1 is equal to, take all the things, 5 minus 4 I2 minus 4 I3. Okay? So that is minus 2 I1. So then what is I1? I1 is simply minus 2 I can take there. So that would be minus, if we take minus there, then what is it? This would be minus, this would be plus, this would be plus now. So I can say 4 I2 plus 4 I3 minus 5 divided by 2 is I1. Okay, so I got I1 here. So once I get I1, now I am expressing I1 in terms of I2 and I3. Okay. Once I get this, wherever I have I1, I can use this. And when I simplify it, I will get this equation in terms of I2 and I3. Likewise, this equation will also be in terms of I2 and I3. Okay. So the moment you get these 2 equations manipulated in I2 and I3, so now you can solve them, right? The 2 I2, I3 equation can be very easily solved for you. Okay? If that is solved, then I2 and I3 can be solved. If I2 and I3 are solved, then I1 can be solved too, using this expression. I hope you understand what I am saying. I1, you expressed I1 in terms of I2 and I3. Now, wherever I1 is in the other 2 equations, put 4I2 plus 4I3 minus 5I2 in this expression and then manipulate it. Then you will get an expression like this. Some number, say A into I1, so I2, and plus some number B into I3 is equal to some number AN1. This is what you will get once you manipulate it. And here also you get some number C to I2 plus some number D into I3 is equal to another number, say N2. See, once you get this expression, you can solve for I2 and I3. This is something that you have done in your 10th standard. So you can find I2 and I3 values. Now once you find I2 and I3 values, come back and find the I1 value. So now you have found I1, I2 and I3. So that is how you do this regular solution. Otherwise, there is this matrix method that can also be used to find I1, I2 and I3. It's up to you. But if you do that, then what happens is that you are getting the values. Okay. Once I've done that, let's see. Like the I1 value. Once I've done this, I1 value is given to be 2.5 amperes, and then I2 value is given to be 5 by 8 amperes. Then I3 value is given to be 8 plus 15 by 8 amperes. 7 by 8. So 15 by 8 amperes. So this is 2.5 amperes, it's 5 by 8 amperes, and then 15 by 8 amperes. So you found I1, I2 and I3 now by solving this equation as I just described. Now once you have solved for I1 and I2 and I3, now you can find the current in all these branches, right? Okay. Where is I1? I1 is this, right? This branch. This branch current is given. It's 2.5 amps. I've used blue. It's a different color. Okay. So this is actually 2.5 amps is flowing through it in this branch. That's what we got. Where is I2? I2 is this. How much is the current flowing through it? It is 5 by 8 amperes. So the current here is actually 5 by 8 amperes. I2 is that. Where is I3? I3 is this. That is 15 by 8 amperes. So that is simply 15 by 8 amperes. So 1, 2, 3 you got. And what about this branch? It's I1 minus I2. What is I1? 2.5. So 2.5 minus 5 by 8. Okay. So what would that be? 2.5, 5 by 8. So 8 into 2.5 would be 4 would be 10, and then 8 would be 20. 20 minus 15 by 8. So this would be 15 by 8. That's the current you will have here. Okay? So that's the current in this branch. 15 by 8 amperes. And what about this is again 15 by 8, right? Okay. So no problem. 15 by 8 will be this. So no issues there. Okay. So what would be this then? This current. The current in this circuit. I2 plus I3 minus I1. Well, you can very easily make out that 15 by 8 is coming here, and then 15 by 8 is going there, because you found 15 by 8 there already. So 15 by 8 is going there, so there could be no current coming through this or leaving through that, right? So this must be 0. The current through this must be 0. But we'll add I2 plus I3 minus I1, right? I2 plus I3. What do you get? I2 plus I3 is 20 by 8. What is I1? I1 again is 2.5. 20 by 8 is again 2.5, right? If I add these two, 5 by 8 plus 15 by 8, I will get 20 by 8, which is 2.5. So 2.5 minus 2.5 will be equal to 0. So the current through this branch is 0. 0. No current is flowing through. Okay. So notice here I have found the current which is flowing through all the branches of the circuit using Kirchhoff's law. Hope this is clear to you.